Hello everyone. Today we're going to talk about exponentials and logs, specifically real-life applications of them. Now, the most common application of exponential growth that you would see just in day-to-day life is probably interest in a savings account. Okay? Interest is compounded, which means every so often the money that you've earned from the bank gets added back to your savings account. Okay, that's called compounding. How often they compound it can change bank to bank, and it greatly affects how much money you have. It's always based on an interest rate. Interest rate is by year, but banks don't have to compound just once a year. They can compound as frequently as they'd like. So let's try a problem. Well, let's look at the formula first. Here's a formula for compound interest. A is your final amount, the amount at the end of the time that you're looking at. P is called the principal, it's your starting amount. 1 plus R. R is an interest rate, and remember, this has to be converted from the percent that's given to you into a decimal. That would be like 2.3%. N is the number of times it's compounded. So if it's compounded quarterly, N would be 4. If it's compounded monthly, N would be 12. And then T is the number of time in years, the amount of time in years. Remember, T is measured in years because interest is calculated in years. You invest $1,000 at 4.8% interest. How much money would you have in your account after 10 years if compounded? Let's start off with yearly. This is called simple interest. So the final amount is the starting amount times 1 plus the rate. I'm not going to put 4.8%. I'm going to move the decimal 2 places and put 0.048%. N is the number of times compounded per year. But if it's only compounded yearly, it means it's compounded once per year, raised to the NT. This is set up perfectly to type in your calculator. So I just went ahead and did that for you. You get $1,598.13. And I'll show you how to type that in the calculator in a second. There's a way to do it that makes it a little bit easier. Semi-annually, so twice per year. Same concept, 1,000, 1 plus 0.048 over, this time it's 2 because it's twice per year, 2 times 10. Now if you want to type that in the calculator to make it easy to work with, we can just go 1,000, parentheses, 1 plus, let's put in our fraction, alpha, y equals 1.048 over 2, parentheses, raised to the 2 times 10. By doing it all in the calculator, it lessens your chance of a mistake. $1,606.94. So 1,606.94. Let's do the same problem, but do it quarterly. Quarterly means 4 times a year. So, as you can see, the setup for these is always very similar. 1 plus R over N to the NT. I'm not going to spend the time typing it with the calculator this time. You can do that yourself. And notice that every time I increase my compounding, I'm increasing my money. That's not a lot, but it is a little bit. So this is yearly, then we did it semi-annually, and then we did it quarterly. You could do it monthly, N equals 12. You could do it weekly, N equals 52. You could do it daily, N equals 365, or N equals 365.25 if you want to be really accurate. What if instead of doing it per day or over time, what if I compounded it continuously? Meaning, as soon as you earn any money at all, it's added back. Well, that's a different formula. So, A is still your final amount, P is still the principal, R is still the rate, and T is still the time in years. E. We talked a little bit about E in Honors Algebra 2. It's kind of like pi. It's a letter that means a number, an irrational number. And it goes on forever without repeating. And here's an example of where that's used in the real world, if I'm compounding continuously. So, I still have $1,000 in my bank account. E, the rate is 0.048, and the time is 10. How do I type that in the calculator? Well, there's an E button on your calculator. So I do 1,000. E raised to the 0.048 times 10. And this is the most money that you can get, $1,616.07. It is the best possible solution for compounding. This is how other things grow, like populations, things like that. So, find an answer to this problem that is accurate to at least 3 decimal places. Be able to explain your reasoning. You invest $500 in a savings account at 5.6 interest. So far, sounds normal. Compounded quarterly, okay, n equals 4. How many years would it take to be worth $1,200? So this time I know the final amount is $1,200. The starting amount is $500. 1 plus the R is 0.056. The N is 4. Raised to the 4. I don't know my time. You have a variable in the exponent. We have a way to solve that, but let's pretend like we don't know how. Okay? I'm going to clean this problem up a little bit. I'm going to divide this over here, so I get 12/5 equals. So I'll clean this up in here. I get 1.014 raised to the 4t. Anytime I have an equation and I want to solve it and I just need an answer, I don't need to show work, I can always use my calculator, put this side in y1, put this side in y2, and let's see where they cross. So grab my calculator. Y equals 12/5. On the other side, 1.014 raised to the 4x. Let's set up a window. X in this case is time, so time has to start at year 0. I don't know how long it's going to take, so I'm just going to guess maybe within the first 30 years, and we'll see if they cross. Y is the amount of this side, so I'm going to start at 0. 12/5 is exactly 2.4, so I need to be a little bit bigger than 2.4, so I'll just put 3 in here. And I can see my graph. The flat line, the horizontal line for 12/5, and then the slowly curving exponential curve for 1.014 to the 4t. Second trace 5, enter, enter, enter. And I get x to be about, t to be about, I guess, 15.743 years. And this is a really good estimation. It's a really good estimation, about 15 years and 9 months. But can we do it algebraically? Well, yeah. The problem is we had an exponent in this problem. We had an exponential equation. What function will cancel out an exponential function? And it's a log. Any kind of log will do. But we're either going to use a common log, which is a log base 10, or a natural log, which is a log base e. And the reason we do that is we have a log base 10 and a log base e button on the calculator. I will usually use a natural log. It will make more sense when you get to calculus why I do that. But either one works. Let's start out simple. Solve the following exponential equation. I could do it with a log, but sometimes I can do it by rewriting the problem. Now what do I mean? Well, I know that I can rewrite 16. 16 is 4 squared. Now look, the bases are the same. They're both base 4. If the bases are the same, the exponents have to be the same. So this exponent is x plus 3. This exponent, I have 2 exponents together, so I'm going to multiply them. 6x minus 4. Now I didn't need a log, and I didn't need to use my calculator. I can solve this like a regular algebra problem. Subtract this over, add this over, divide, x equals 7/5. I didn't need to do a log because I could rewrite the bases. What about here? Well, you can't raise 8 to a pretty power and get 16, but you can rewrite them. 8 is 2 to the third. 16 is 2 to the fourth. I have a base of 2, so I'll look at my exponents. Multiply them, that's 3x minus 21. That's 4x plus 12. Solve it like a regular algebra problem. X equals negative 33. Again, I didn't need a log because I could rewrite 8 and 16 as the same base. But that doesn't always work. No matter how much you try, you cannot rewrite 2 and 5 as the same base. So what can we use to eliminate the exponential part of this equation? We're going to take a log of both sides. I'm going to use a natural log. Again, it'll make more sense when you take calculus why natural log is better to use. It's also just easier to write. If I do it to the same thing to both sides, that's legal. Remember, there's a power, a property that you have of logs. When there's an exponent inside the log, I can move it out to the front. So I've got x plus 4, natural log of 2, equals 4x minus 3, natural log of 5. Now from here, it's a lot of algebra, but it's stuff you've done before. I see something outside of parentheses, I'm going to distribute it. X natural log of 2 plus 4 natural log of 2 equals 4x natural log of 5 minus 3 natural log of 5. Let's get all my x's on one side, everything else on the other. So I'm going to move this over here. X natural log of 2 minus 4x natural log of 5 equals, this needs to move over, negative 4 natural log of 2 minus 3 natural log of 5. Notice, this problem could have been done differently. I could have moved this x over here and this over here, and everything would have been positive. So there's two ways to do this problem, but you end up with the same answer. Both of these have an x in it, so I'm going to factor the x out. And I want the x by itself, so I'm going to divide what's in parentheses over. Now this looks really ugly, and it is. But it is the only way to answer this question exactly. Kind of like if you got the answer square root of 5, you wouldn't try to turn square root of 5 into a decimal. This is a really ugly answer. It would be a really ugly decimal, but this is the exact correct answer. So where would I ever use this in a real world problem? This problem we did earlier. Okay? This is the same problem. We want the exact solution to it. Well, we said it was 12 fifths equals 1.014 to the 4t. We graphed it to solve it. This time, I'm going to take a natural log of both sides. So I've got natural log of 12 over 5 equals, remember, I have a power, I can move it in front, 4t natural log of 1.014. I want the t by itself. So on this side, I'm still going to have the natural log of 12 fifths. Divided by, I got to get rid of the 4 and the natural log of 1.014. That is the exact answer. The last answer was rounded. This is exact. Manipulating logs is not that hard. Just remember, take a log of both sides and move your powers out front.